Okay, so let's see some questions from sheet metal operations of GATE exam. So the first question you can see here, a strip of thickness 40 mm is to be rolled to a thickness of 20 mm using two high rolling mill and having rolls of diameter 200 mm. Correct? So here we need to find out the coefficient of friction and arc length in millimeter. So you can see here, if I write its solution, then you can see. So first you write what are the given in the question. So the thickness means h naught. This is original dimension which is given here. H naught is given here. That is original height of the strip, that is 40 mm. And after rolling the height, that is the final height is 20 mm. Is it clear? And you can see here the rolls diameter. You can see here. Here we have diameter which is equal to 200 mm. But in our formula we need radius. So can I say this is nothing but this is half of the diameter, that is 200 by 2. This is equal to 100 mm. Is it clear? So we need to find out the coefficient of friction, and we also need to write projected length of contact. Yes or no? Is it clear? So if I write the self entry condition, if I use, so simply here we have one relation, that is mu square into r should be equal to delta h. Yes or no? So from this, if I write mu, which is equal to square root of delta h by r, correct? And now if you put these values here, then you will get the coefficient of friction. And let us suppose delta h is nothing but this is h naught minus hf. So simply can I write this is 40 minus 20. This is delta h over r. A radius is given, that is 100. So if you simplify this, then you will get mu is equal to 0.45. Correct? And after getting mu, here we need to calculate the arc length. Correct? So let's say this is LP, which is nothing but the square root of R delta H. Is it right? So LP is equal to radius is given, that is 100 mm. And what about delta H? This is H naught minus HF, that is 40 minus 20. Yes or no? So now if you simplify this, then you will get this answer. You can see here, that is 44.72 millimeter. Is it clear? So this is the right one. So according to this, the correct answer is option D, where mu we have that is 0.45 and the projected length is 44.72. Let me check once. You can see here, this is 20 over 100. Square root of this is 0.2. This, yes, 0.447. Yes, this is 0.452. Yes, it is right. Okay, so let's see another question. The percentage scrap in a sheet metal blanking operation of a continuous strip of sheet metal as shown in the figure. So let us suppose if I consider this portion, percentage scrap we need to calculate. So if I say, if I assume this section only, so this is the total area. So, and what about its length and height? So you can see we have this rectangle. We have this rectangle. You can see here. Then if I write its length and height. So you can say this is d by 5. You can say here this is d by 5 and this is half of the diameter. So d by 2 plus d by 2 plus d by 5. So this is nothing but this is d plus d by 5. So simply can we write 6d by 5. Correct? And similarly, if I write height, so you can say this is d by 5 and this is d by 5 and this is total diameter. So this is nothing but it can be written as d plus d by 5 plus d by 5 and this is equal to 7d by 5. Is that clear? So now if I write the total area of the strip is equal to 6d by 5 into 7d by 5. So it can be written as 42d square by 25. Correct? But out of this, you can see out of this strip, this is our useful part. That is our area of circle. Correct? And since this is blanking operation, so obviously our objective is to cut the blank. So area of blank, if I write area of blank, so this is nothing but it can be written as pi by 4 d square. Yes or no? So this is our useful area. So if we want to write the percentage scrap, so percentage scrap is nothing but this total area. Let's say it is represented by area T minus blank area of blank, that is useful part, over total area into 100%. So this gives us the maximum proportion, the percentage of scrap. Is that clear? So here we have this is 42 times d square by 25 minus 5 by 4 d square over 42 d square by 25 into 100%. So now if we calculate, so let's see how much we get. How much scrap we get. This is equal to, let's see, this is 40. You can say d square from this expression, it is cancel out because in the numerator denominator we have d square. So this is 42 by 25. So this is 1.68. 1.68 and pi by 4 is nothing but 0.7856 over 1.68 to 100. The value of pi by 4 is 0.786. 7856. So this is 53 point. After calculating this, here we get 53.238%. 53.28%. Is it clear? 53.28%. Is it clear? And this is the right answer. And this is the right answer. Is it right? So I think all of you getting how to solve this question. Is it right? Okay. Okay. Let's see another question. A 10 millimeter deep cylindrical cup. A 10 millimeter deep cylindrical cup with a diameter of 15 mm is drawn from the circular blank. So 10 mm deep cup. So if I draw a cup, so this is the cup. Correct? And its height is nothing but this is equal to 10 mm. From with a diameter of 15 mm, so its diameter is 15 mm. neglecting the variation in the seed thickness, the diameter of the blank. So for making this cup, what is the size of this blank? This is a blank and its a diameter is d. So we have direct relation, that is capital D is nothing but this is square root of d square plus 4dh. So now if we put the value of d and h on this expression, where small d is nothing but this is diameter of the cup and h is the height of the cup. So this is 15 square plus 4 into 15 into 10. So now if you simplify this, then here we get, let me check, 15 square plus so here we get 28.72 mm. So this is the right answer. This is the right answer. Is it clear? So this is very simple question. Okay, let's see another question. In a sheet metal of 2 mm thickness, of hole of 10 mm diameter needs to be punched. So you can see this is a punching operation. Here our prime objective is punching. Sheet of 2 mm thickness. So thickness of the sheet is given. Let's say this is 2 mm and the hole size, that is diameter of the hole, diameter thickness, a hole of 10 mm diameter needs to be punched. So diameter of hole, this is 10 mm. The yield strength in the tension of the sheet is, that is S by T, which is 100 megapascal, and ultimate shear strength, that is SUT, and this is shear strength SUS. Is it clear? Yield shear strength, this is 80 megapascal. The ultimate shear strength is 80 megapascal. The force required to punch the hole. So here we need to calculate punching force. Yes or no? So you can see here, actually, if I draw it's a top view, then it is looking like this. Here we need to make a hole whose diameter is dh, and if I say it's cross-sectional view, then it is looking like this, and its thickness is 2 mm. Yes or no? So from this, if I calculate shear area, so can I say the perimeter of the circle, that is pi d h into thickness, this is called as shear area? Yes or no? So the punching force required to shear out this material is equal to SUS, yield shear strength of the material, into shear area. So this is 80 into shear area is pi, dh is 10 millimeter and thickness is 2 millimeter. So when you calculate this value, then here we get, let me check, 80 into pi into 20. So simply here we get 5 in kilonewton. So for determining this value in kilonewton, so simply we divide 1000. So this value becomes in kilonewton. So from this here we get 5.024 kilonewton. So from this FP is nothing but this is 5.024 kilonewton. This is the right answer. This is the right answer. Is it clear? Okay, so let's see another question. A rectangular hole of size 100 mm by 50 mm. So let's say this is a sheet in which we make a rectangular hole whose size is 100 mm by 50 mm. This is 100 mm and this is 50 mm. Having to be made of 5 mm thick sheet. So the thickness of the sheet is nothing but 5 mm. Correct? Still having ultimate tensile strength means SCOT, this is 500 megapascal. Next, shear strength, ultimate tensile strength and shear strength means SUS is nothing but this is 300 megapascal. Respectively, the whole is made by punching process, neglecting the effect of clearance, the punching force required. So once again, we need to calculate punching force in kilonewton. So punching force is nothing but it can be written as yield shear strength into shear area. So yield shear strength is 300 megapascal. And what about shear area? Shear area is nothing but if I write shear area from this, so this is nothing but this is perimeter of the rectangle into thickness. And what about perimeter? So perimeter is nothing but 2 times of 100 plus 50 and thickness is 5 mm. Correct? So from this you will get 150 into 2, that is 300. 300 into 5, 1500 millimeter square. 1500 millimeter square. Yes or no? So now if you simplify this, and obviously here we need to calculate this value in kilonewton. So simply if I divide with 1000, so this value becomes in kilonewton. So the punching force required is nothing but this is 450 kilonewton. 450 kilonewton, that is option B. That is option B. Yes or no? So when if you listen, whenever you perform punching operation, we always write this expression. This is generalized formula, and obviously the perimeter for different section we have different value. So since here we have a rectangular pocket, so for this the perimeter is 2 times of length plus width. And if it is circular, then instead of writing this, you just write pi d. Pi d is a perimeter of the circle. Is it clear? Okay, so let's see another question. Calculate the punch size in millimeter for a circular blanking operation for which details are given below. The size of blank is given. Calculate the punch size in millimeter for a circular blanking operation. This is the key point. This is a blanking operation. First to write, this is a blanking operation. Is it clear? And why I am interested in this? Because in the blanking operation, the diameter of the hole, diameter of the blank, not hole, diameter of the blank is always equal to the diameter of the die, and this is always fixed. This is always fixed. Is it clear? So this is a blanking operation in which the blank dia is 25 mm. Blank dia is 25 mm. And remember, this is the key point, correct? Whenever you find this kind of question, so first you see whether this problem belongs to blanking or punching, correct? And the thickness of the sheet is also given, that is T is equal to 2 mm. Radial clearance between the punch and the die means this is C1. Let's say this is C1 radial clearance, which is 0.06 millimeter. And the die allowance, that is A, is given here, that is 0.05. So we need to find out punch size. We need to find out the diameter of punch. So remember, the diameter of punch is nothing but this is the diameter of the die minus 2C1 minus A, that is clearance, die allowance. Is it clear? And I already told you the diameter of the blank die is nothing but this is diameter of the blank. So simply can I write this is 25 minus 2 into 0.06 minus 0.05. So when you calculate this value, then here we get this answer. 2 into 0.06 plus 0.05 and 25 minus this. So 24.83. Diameter of the punch is 24.83 millimeter. 24.83 millimeter. Is it right? So according to this, the correct answer is option A. So you can see here, this is the key point. Whenever you write question like this, then first you find whether this operation belongs to blanking or punching. Is it clear? Okay, so let's see another question. A disc of 200 diameter is the blanked for from a strip of aluminum alloy of thickness 3.2 mm. A disc of 2 mm diameter. So the diameter of the blank is given here, that is 200 mm, and the thickness is also given here, that is 3.2 mm. The material shear strength tau s is given, that is 150 megapascal. The blanking force, we need to calculate blanking force. So blanking and punching both are shearing operations. So for determining blanking force or punching force, we have same relation, that is shear strength into shear area. And since here we need to make a disc which is circular in size and its thickness is 3.2 mm. This is thickness and its diameter is diameter of the blank. So if I write shear area, so simply you write perimeter of the circle into thickness, and perimeter of the circle is pi db into thickness. Yes or no? So simply if you put these values here, this is 150 into, what about this area? Pi into db, which is 200 mm, into thickness, that is 3.2 mm. Correct? And obviously we need to calculate this value in kilonewton. So simply here we divide with 1000. So now after calculating this, how much we get? So let's see, this 0 and this 0 is cancelled out with this, and this 0 is cancelled out with this. So simply here we get 15 into pi into 2 into 33.2. So here we get 301. 301.44 kilonewton. This is the right answer. This is the right answer. And according to this, the correct choice will be option B. Okay, so let's see another question. A blank of 50 mm diameter, is to be sheared from a sheet of 2.5 mm. So once again, this is a blanking operation in which the diameter of the blank is given, that is 50 millimeter, is to be sheared from a sheet of 2.5 mm thickness. Thickness is also given here, this is 2.5 mm. The required radial clearance between the die and the punch is 6% of sheet thickness. This is radial clearance. Radial clearance means C1, and this is 6%, means 6 by 100. Is it right? 6 by 100 into sheet thickness. So this is 2.5. Correct? So if you simplify this, then here we get 150 by 1000, or simply you can say 0.15 mm. Yes or no? 0.15 mm. This is radial clearance. The correct, the punch and die diameter. So once again, you can see this is a blank of this, means this is a blanking operation. The blanking operation. Is it clear? From the question, first you need to identify whether it is blanking or punching. So this is blanking operation, and for the blanking operation, the diameter of the blank, must be equal to the diameter of the die. Yes or no? And this is fixed. Is it clear? So from this, simply can I write the diameter of the die is nothing but this is 50 mm. So here we need to calculate the diameter. Let's see if I write in capital letter. Correct? diameter of the blank is equal to diameter of the die. So the diameter of die is 50 mm, correct? So now, once you get the diameter of the die, so diameter of the punch is nothing but this is diameter of the die minus 2c, and this is 50 minus 2 into 0.15. So it can be written as this is 49.7 mm. 49.7 mm. This is diameter of the punch. So while giving the answer, first you see, we need to represent the diameter of the punch and the die. The diameter of the punch is 49.7 and the diameter of the die is 50.00. So the correct answer is option C. Okay, so let's see another question. Match the following wrinkling. You can see here we have defects and here we have process. So wrinkling is a deep drawing defect, yes or no? And barreling is a upsetting defect. And cold shut is a closed eye defect. So obviously the center burst is the exclusion defect. So E2, C3, R1 or S4. 2314, 2314, 2314. So option C is the right choice. 2314. Yes or no? Correct. Okay, so let's see another question. A circular blank of 35 mm diameter are punched from a steel sheet of 2 mm thickness. If the clearance per side between the punch and the die is to be kept as 40 microns, circular blank of 35 mm diameter are punched from steel sheet. So this is a blanking operation. So don't be confused. This is blanking operation. Is it clear? And the diameter of the blank is already given here, which is equal to diameter of the die, and this is equal to 35 mm. Is that right? Are punched from the steel sheet thickness. Thickness is given, that is 2 millimeter. If the clearance per side between the punch, per side means this is a radial clearance. Between the punch and the die is to kept 40 microns. This is already given here, 40 microns. 40 to 10 power minus 3 millimeter. So simply it can be written as 0.04 millimeter. The size of the punch and the die. So we need to write diameter of the punch and diameter of the die. So obviously the diameter of the die is already given here, that is 35 mm, because this is a blanking operation. So the diameter of the punch is nothing but this is diameter of the die minus 2c. So this is 35 minus 2 into 0. This is 2c1, 0.04. So simply it can be written as 34.98 mm. This is diameter of the punch. So first we need to give the answer of punch. So 34.9, sorry, 92, not 98. This is 92. 34.92 and 35. Yes, option B is the right answer. Option B is the right answer. Yes or no? So don't be confused whether it is punching or blanking operation. You just see here in this, the size of the blank is given. This means the objective of this process is to create a blank. So this is the blanking operation. Is that right? Okay, so let's see another question. A cup is to be drawn to a diameter of 70 mm with 35 mm depth. So the diameter of the cup is given, that is 70 mm, and the diameter and the height of the cup is also given here. This is 35 mm. That's from 0.5 mm thick sheet. Thickness is also given here, that is 0.5 mm. The cup is drawn in one operation, assuming sigma u is equal to 430 megapascal. The maximum drawing force. So if I write drawing force, so this is nothing but shear strength, sorry, this is sigma u into shear area. So simply we can write this is 430 into cup is drawn to a diameter of 70 mm with 35 mm depth. Is it clear? So you can see here the maximum, here we need to calculate maximum drawing force. Is it clear? Maximum drawing force. So first here we need to calculate the diameter of the blank, correct? Because the drawing force is nothing but this is 430 into pi d into t. So first we need to calculate diameter of the blank. So from this, the diameter of the blank, this is nothing but it can be written as, we already know this formula, square root of d square plus 4dh, where d is the diameter of the cup. So you just put the value here, then simply here we get 70 square plus 4 times 70 into 35, correct? So from this here we get 70 square plus 4 times of 70 to 35. So simply here we get the diameter of the blank is nothing but this is 121.24 millimeter. So you see this is a blank on which you need to apply a force through a punch. Is it clear? If I draw its figure like this. So for the better understanding, let's say this is a blank in which you need to apply a force with a punch of size this. The punch, correct? And this is the blank whose diameter is capital D and thickness is T. Yes or no? That's why I'm writing this formula. So FD is equal to 430 into pi into 121. Yes or no? Pi into 121.24 into thickness is already given here. It is 0.5. 0.5. Yes or no? So when you calculate this, then here we get 0.082 mega Newton. 0.82 mega Newton. Here we need to write this answer in mega Newton. So 0.082 mega Newton. So option B is the right choice. So first you need to calculate the diameter of the blank. Then you just put this value on this expression. Then you will get the answer. Yes or no? And similarly, you can see this question. A cup is to be drawn of diameter 70 mm with 35 mm depth and thickness 0.5 mm. The cup is drawn in operation assuming sigma is equal to this, the required blank diameter. Okay, so this is the first part of the previous question, and the previous question was the second part. Is it clear? So for this, you need to write the diameter of the blank, which is nothing but this square. This is square root of d square plus 4dh. And now if you put this value here, then we already calculated this value. Is it clear? This is 70 square plus 4 times of 70 into 35. So obviously here we get d is nothing but this is 121.24 mm. This is the diameter of the blank. So actually this is first part of the previous question, correct? And the previous question was the second part. Okay, so let's see this question. It is required to punch a hole of diameter. You can say required to punch a hole. You can say of diameter 10 mm. So this is a punching operation. This is a punching operation. Is that clear? This is a punching operation whose diameter of the hole, which is equal to diameter of the punch, which is 10 millimeter. It is already given here. On the sheet of thickness 3 millimeter, the shear strength of the material is already given here, that is 420 megapascal. The required punching force, actually we need to calculate here punching force in kilonewton, correct? So the punching force is nothing but this is shear strength into punch shear area, correct? So simply can I write directly, that is 420 into pi d, circumferential length is pi d into thickness, that is 3 mm. And since we need to put this value in kilonewton, so we just divide with 1000, correct? So after calculating this, here we get Fp is equal to 420 into 3.14 into 30 over 1000. So this is 39.564, 39.564 Newton. This is the answer. Is it clear? This is the answer. So correct answer is option B. Okay, let's see another question. Okay, so match the list to match the item in group 1 and group 2. So in group 1, the yield point elongation, spring back, wrinkling and residual stresses. So yield point elongation belongs to leader band, slipping of leader band. Spring back, we don't know. What about wrinkling? And what about residual stresses? So let me check. E2, so we have only two options. So the option A is wrong. This is also wrong. Spring back mainly causes in plastic deformation. So Q3. Is there any option? Yes, Q3. And wrinkling is mainly happens in distortion of the dimension or compressive stress. So actually, this is not appropriate answers. We don't have any appropriate options. Correct? Because wrinkling is nothing but this is non-uniform deformation. Distortion of the dimension can be same. That is R1. R1. Correct? Wrinkle is a what do you mean by wrinkling? Actually, you can see when you make a cup like this. Correct? This is a cup in which we have a flange. So due to insufficient blank holding force, the flange may made like this. This defect is called as wrinkling defect. This is called as wrinkling defect. So non-uniform deformation on the flange region is called as wrinkling defect, and it is mainly caused due to insufficient blank holding force. Correct. So the most appropriate option for the wrinkling is distortion in dimension. And obviously yield point elongation. Actually, Luder band is nothing but, you see, when you have stress strain diagram, after upper yield point, here we have this phase, and this is called as slipping of Luder band. This is called as slipping of Luder band. Is that clear? Now, if I talk about residual stresses, then obviously residual stresses induced. Residual stress can be said this is a compressive stress, S4. So there is no option S4. So most appropriate answer will be residual stresses. Either it can be 1, 2 or 3. 1 means distortion of dimension, this is not correct. And 2, that is Luder blank, this is also not appropriate. And 3, that is plastic deformation. Yes, the residual stresses may induce in the plastic deformation. So none of the option is correct. So if you give most appropriate answer, so you just select yield point elongation is called as Luder band, slipping of Luder band. And with respect to this, if I give the answer, then here we have P2 and spring bracket is 3. So the correct answer is option C. Correct, because we none of the correct answers, कोई भी आंसर यहाँ पे perfectly correct नहीं है. So here we need to choose most appropriate answer only. Okay, so let's see. Okay, so this is not a part of sheet metal operation, so just I am leaving these two questions. Okay, so next question you can say here. A 525 mm hole is pierced in a T of 25 mm thick steel sheet having a shear strength. So you can see here our objective is to make hole. So diameter of the hole is 25 mm. And since our objective is to hole, so simply can I say this is a blanking of, sorry, this is a punching operation. This is a punching operation, yes or no? Because here our objective is to make a hole. And whenever we have an objective of making hole, then it will be considered as a punching operation. And in punching operation, the diameter of the hole must be equal to the diameter of the punch, and this is fixed. And this is fixed. Is it clear? And the shear strength is also given, that is 350 megapascal. If the diametral clearance is given, you can see this is a diametral clearance which is C is equal to 2 times of C1, which is already given here, that is 0.0064 into T square root of tau. Yes or no? So here we need to find out the diameter, the die diameter and punch diameter. Here we need to find the die diameter and punch diameter. So punch diameter is already given here, that is 25 mm. So our objective is to find out the die diameter. So first we need to calculate diametral clearance. This is C is equal to 0.0064 into sheet thickness is also I think given, that is 2.5 mm. I forgot to write, this is T is equal to 2.5 mm. Correct, 2.5 mm into square root of tau, and shear strength is also given, that is 350. So let me check if I calculate this value. So simply here we get square root of 350 into 2.5, so 0.0064. So this is nothing but C is equal to 0.299. Correct. And once you get this, so the diameter of the die is nothing but this is diameter of the punch plus clearance, diameter clearance. So this is 25 plus 2. This is right or not? Let me check. This is square root of 350. Yes. Into 2.5. Yes. Into 0.0064. 0.29, yes, it is right. 0.299. So this becomes 27.99 millimeter. So the diameter, the die diameter and punch force also we need to calculate. So the diameter of the die have only 2 zeros. Let me check once again. That is 0.0064 into sheet thickness, that is 2.5 into square root of The yield shear strength, that is 350. So after calculating this, yes, 0.299. So the diameter of the die is 27.99. So first you need to represent diameter of the die. So this is wrong answer. I think we have some error in this question. Instead of writing 0.0064, I think we have 0.00064. Cos 25.3 is the right one, but this is 2.33. So might we have some mistake in this question? Correct, because if I calculate this value, then here we get okay. Oh, this is my mistake. This is 25 plus 0.299. Now it is right. 25.299, or approximately we can say 25.3. Is that clear? 299, or approximately we can write 0.3. So the die diameter is 25.33, yes, and the punch diameter is 25 mm. So need not to calculate punch force, although we can calculate. This is not a big deal. You can see here, but need not to calculate it. Yes or no? If I write the punch force, so can I say FP is equal to shear strength into shear area, and into diameter of the hole, and diameter of hole is 25 mm and thickness is 2.5. So when we calculate this value, then here we get uh, in kilonewton. If I write, so if we divide with 1000, so simply here we get FP is nothing but this is 68.687 kilonewton. So according to this, the correct choice will be option D. The correct choice will be option D. Yes or no? So like this, you can calculate this value. Yes or no? Okay, so let's see another question. In a deep drawing of sheet metal spring-loaded stripper, clamp the work until the punch penetrates twice the stock thickness. It removes wrinkles on the product edge. Shader removes the work from the tool, and punch is completely withdrawn from the work material. So the correct answer is option B. You can see the stripper is mainly used to hold the blank while the return of the punch or withdrawal of the punch. So the correct answer is option D. Determine the load required to punch of 20. You can say this is a punching operation. So a 20 mm diameter. So the diameter of punch, diameter of the hole, sorry, diameter of the hole 20 mm. This is punching operation, and the sheet thickness is 2 mm. The properties of the material of the sheets are given here. Here we only use this stress. Why I am writing apart from this yield shear strength, which is 350 megapascal. I'm only interested for this value. The load in kilonewton. So we need to find out punching load in kilonewton. So FP is nothing but this is tau s into pi dh into thickness. So this is 350 into 20 into pi into 20 into 2. And obviously if we divide this value with 1000, that we get in kilonewton. Is that right? So from this FP is nothing but you can see here 350 into pi into 20 into 2 4,000. So this is 43.96 kilonewton. So don't be confused with these number of values, correct? So only we use this value because in the punching operation the metal gets shear out. So here we need to use shear strength only. According to this, the correct answer will be 43.9 Newton. And I think when you use 250, then you will get this value. When you use 410, then you will get this value. And so for every cases, the answer is given here. So don't be confused. Correct? Okay, so let's see another question. A hole of 40 mm diameter is pierced in a steel sheet of 4 mm thickness without shear on the tool. The shear strength of the steel is 40 Newton per millimeter square. The penetration is 25%. What is the expected percentage load reduction of the shear 1 mm punch? Okay, so a hole of 40 mm diameter is pierced in a steel sheet of 4 mm thickness without shear. So it means you have a punch like this, and in the another case you have a sheared punch like this, and the value of shear is nothing but this height is called as shear, which is given here 1 millimeter. So if I use this is case 1 and this is case 2, so first we calculate load for case 1. So this is nothing but shear strength into a hole, so this is pi d into t. So F1 can be written as this is 400 into pi into 40 into sheet thickness is 4. So F1 is nothing but simply here we get 400 into 0.34 to 40 into 4. So here we get, simply here I am writing in Newton only. So 20960 Newton. And with shear if I calculate, so this is nothing but this, and the penetration is 25% of sheet thickness. Penetration is, so simply here we also need to multiply one factor, that is 0.25, because you can see it. What do you mean by this? So let's see. If you have a sheet like this and you need to cut a hole from this sheet whose thickness is 4 mm, so how much shear is actually required? T is 4 mm. When your tool penetrates up to 25 thickness only, means up to this height, correct, then the complete shearing action takes place. So that's why here we need to, right, we need to multiply this 0.25 also with this value. So this becomes 5240 Newton. And if I use with shear, so can I write F2 is nothing but tau s into pi into d into t into penetration p over s. So F2 is nothing but s plus total penetration, correct? So this is 400, and you can see the capital P is nothing but this is sheet thickness into percentage penetration, that is small p, which is 25% already given here. 400 into pi into d, that is 40 mm, into t, that is 4 mm, of 25% penetration, that is 0.25 over 1 plus shear. The amount of shear is given, that is 1 mm plus 4 into 0.25, correct? So once you calculate this values, then how much we get, you just see. So after calculating this, here we get this answer 25120 Newton. So if you use sheared punch, then this much amount of force required, and if you use without sheared punch, then this much amount of force actually required. So here we need to calculate what is the expected percentage load reduction. Expected percentage load reduction. So simply if I write percentage load reduction, then obviously this is a 50%, correct? So F1 minus F2 over F1 into 100%. So when you put this value, because F2 is a half of F1, that's why I'm writing like this. So here we get 50% reduction. 50% reduction. Yes or no? So the correct answer for this question is option C. The 50% reduction takes place. Means if you use sheared punch, then only 50% load is required as compared to previous one. Is it right? Okay, so let's say my question. A cylindrical cup of 48.5 mm diameter and 52 mm height has a corner radius of 1.5 mm cold rolled steel sheet of thickness 1.5 mm used to produce the cup. Assuming trim allowance as 2 mm per 25 mm of cup diameter, what is the blank size? So if you calculate the blank size like this, then simply we can use this relation. Actually, if you calculate the size of the blank without using any clearance, then you will get the same answer instead of using radius, corner radius. So you just see it. The cylinder cup diameter is 48.5 mm, and the height of the cup is given, that is 52 mm. Correct? So you can see here, since the diameter of the cup that is 48.5 mm is greater than 20 times of corner radius, which is the cold rolled steel sheet of thickness. Corner radius is 1.5. Is that clear? Therefore, the blank size, since you can see here, when you have this diameter of the cup is greater than the 20 times corner radius, then for determination of blank diameter, simply we use this relation only. That is d square plus 4dh. Is that right? And if it is less than, then we also include minus 2 times of corner radius. Yes or no? So this is different thing. Correct? So you can see here, this 48.5 whole square plus 4 times of 48.5 into h, that is 52 mm. So when you simplify this, then you will get 111.53 mm. And after this, you need to calculate trim allowance. So trim allowance is nothing but this is 2 mm per 25 mm of cup diameter. Correct? So the cup diameter is 48.5. So can I say this is 2 mm per 25 mm cup diameter? So for unit, can I write this is 2 by 25 into 48.5? Yes or no? So when you calculate, obviously you can see here, if you have cup diameter 25 mm, then the trim allowance will be 2 mm. So if we have 1 mm cup diameter, then how much trim allowance is given? That is 2 by 25. So what about 48.5 mm? So obviously 48.5 mm cup diameter requires 48.5 mm into 2 by 25. Yes or no? So when you calculate this value, then here we get this is equal to 3.88 mm. 3.8 mm. This is trim allowance. Trim allowance means this much amount of the material we need to trim for getting the desired surface finish. 3.8 mm. Correct? So the total blank size is nothing but this is equal to 111.53 plus trim allowance, that is 3.88. Means you suppose you need this much amount of blank. This diameter of the blank is actual requirement. Blank required to make a cup. Correct? So, but for getting better desired surface finish, we need to trim this material. Much amount of material we need to add. Correct? So when you add this value, so this becomes 115.41 mm. 115.41 mm. So the correct answer is option D. Is it clear? So like this. So once you need to check whether the diameter of the cup is greater than 20 times of corner radius or not. If it is greater than corner radius, then simply you use this relation for determining the size of the blank. Is it clear? Okay, so let's see another question. It is required to punch a hole of diameter 10 mm on a sheet of thickness 3 mm. So once again, the diameter is given, that is 10 mm, and the sheet thickness, that is T, is also given here. This is 3 mm. The shear strength is already given here, that is 420 megapascal. The required punch force, here we need to calculate punch force in kilonewton. So the punch force is nothing but this is shear strength into shear area, that is pi d into T. So simply you get here 420 into pi into 10 into 3. Correct? Divided by 1000. Why I am dividing 1000? Because we need to represent this value in kilonewton. So once you calculate this value, so here we get, let me check, 420 into pi, that is 3.14 into 10 into 3 over 1000. Yes, so 39.54, 564, 39.564 kilonewton. So according to this, the correct answer will be option B. So what about this? Consider the following statement related to piercing and blanking. Shear on the punch reduce the maximum cutting force. Yes, this is right. Shear increases the capacity of the press needed. No, this is wrong. Shear increases the life of the punch. Yes, this is right. Total energy needed to make the cut remain unaltered due to the provision of shear. Correct? So here on the punch reduces the maximum cutting force required. The option 1 is the right. Shear increases the life of the punch, so we don't have such any proof. But yes, we can calculate, we can say the shear on the punch reduces the maximum cutting force. So 1 is the right. Shear increases the capacity of the press needed. So you can see here. So if I talk about this question, so the first option is the right, second option is the wrong. Shear increases the life of the punch. We don't know about this. We don't have any evidence whether the tool life will be increases or not. The total energy needed to make the cutting remains unaltered. The energy needed to make the cutting remains unaltered due to the provision of A. Yes, this is the right answer. The total energy will be remain same. So is there any option? Yes, option B is the right one. So the correct answer is option B. 1 and 4 is the right answer. Is it clear? Hydraulic press is used to produce circular blank of 10 mm diameter from a sheet of 2 mm thickness. The shear strength is given here. The shear force required. Many times we see this kind of question, correct? So the diameter is 10 millimeter, thickness is 2 millimeter, correct? And the shear strength of the sheet material is 400. So tau is also given here, that is 400 Newton per millimeter square. The force required for the producing a circular blank. So actually we need to calculate this force. So the force is nothing but this is shear strength into pi dt. Is it clear? So the tau is 400, pi diameter is 10 and thickness is 2. So if I calculate this value, then how much we get? And yes, we need to represent this value in kilonewton. So simply if we divide with 1000, then we get in kilonewton. Yes or no? So let me check what is the correct answer. This is 400 into 3.14 into 20 divided by 1000. So yes, this is 25.12. Yes, we have this option, 25.12 kilonewton. Correct. So the correct answer is option B. So the correct answer is option B. Next, you can see in a sheet metal working, the spring back increases when. Spring back means when you apply load, then material get deformed. But since in the material we have some amount of elastic deformation, so because of this, the material get recover some amount of dimension. Yes, sir. So this is called as spring back, and the ratio of bend radius. You can see the ratio of bend radius. So in sheet metal working, the spring back increases when ratio of bend radius to the sheet thickness is small, the Young's modulus of the sheet is low, the yield strength of the sheet is high, the tension in the applied during bending. So you can see if you have Young's modulus, more Young's modulus, then more spring back takes place, and yield strength of the sheet is high. Yes, obviously if you have higher yield shear strength, then more elastic strain energy will stored. Yes or no? Let's say if you have this material and if you have this material, correct? Then obviously if I compare in both the materials, so in this material we have this is S by T and in this we have S by T. So obviously the first case will store more strain energy up to elastic limit as compared to 2. So Q and R both are the right answer. Tension is applied during the bending. This is not depends upon this. Applied load पे depend नहीं करता है spring back. So S option is the wrong. So if S option is wrong, so this is wrong answer. This is wrong answer. QR is here. Now the ratio of bend radius to sheet thickness. Yes, it also depends upon this. So the correct answer is option A. Correct answer is option A. Okay, next question. In the metal forming operation, the true strain in the x direction is 0.3 and y direction is minus 0.1. The true strain in the z direction is. So let's see here. So the two, you can see in the metal forming process, in metal forming process, the change in volume is always equal to 0. Remember this thing. And I already told you many times, the change in volume is always we have 0 in sheet metal operation. Here we use volume constancy, law of volume constancy, means volume is remain constant. And if volume is remain constant, so simply can I say, so the sum of the strain, the volumetric strain is also 0, because volumetric strain is nothing but this is delta by V, and if delta V is 0, so EV is also 0, and the volumetric strain is nothing but this is Ex plus Ey plus Ez, and this is equal to 0. Yes or no? The algebraic sum of the strain is also called as volumetric strain. So yes, the strain induced along x direction is given, that is 0.3, and along the y direction this is minus 0.1, then Ez is equal to 0. So after simplifying this, here we get Ez is equal to minus of 0.2, minus of 0.2. Is that clear? So the correct answer is option B. This is the very basic concept which is used in the metal forming process. We always use law of constancy of volume. that clear? And okay, so let's see another question. A hemispherical hemispherical of radius r is formed in a press working operation. The radius of the blank would be. So you can see these types of question you need to remember, because uh, we don't have any such proof for this. So you just remember. Or obviously you can see here a hemispherical cup of radius r is formed in the press working. Hemispherical cup, correct? The radius of the blank would be. So whenever we write this, so you need to use this concept. The volume, already we saw the volume in the metal forming is always constant. Means V naught is equal to V final. Initial volume is equal to final volume. So initial volume, if I say if I talk about initial volume is the volume of blank. Let's say this is the volume of blank and this is the volume of hemispherical cup. The volume of the blank is nothing but this is pi by 4 d square into thickness. And what about the volume of sphere? So this is 4 pi r cube, and this is the volume of total sphere. So if I divide with 2, then this is called as volume of hemisphere into thickness. So, 4 pi square by 2, actually surface area into thickness. 4 pi square into thickness. 4 pi square by 2 into thickness. Is it clear? So thickness is cancelled out with this. So that and you can see here we have pi by 4 and here we have pi by 2 only. So can I multiply and divide with 2? So this pi by 4, this pi by 4 is cancelled out. So d square can be written as 8 times of r square. Yes or no? 8 times of r square. So simply from this, the diameter can be written as square root of 8 r square, or we can say, and obviously if you represent this in terms of radius, so the radius of, actually here we need to find out radius of the blank, which is r capital R by 2, and this is 2 root 2 times of small r. So why I am writing this? This is d, and d is nothing but this is 2 times of r. So this 2 is cancelled out with this. R is nothing but this is root 2 times of r. So this is very simple question. You just equate the volume. Yes or no? So the correct answer is root 2r. Okay, so let's see another question. Calculate the smallest punch diameter that can be designed for piercing sheet metal strip with the following data. The pressing strength of the punch is given here. Correct. Pressing strength of the punch is given here. Correct. 1500 megapascal. The thickness of the sheet is 2 mm. Factor of safety is 3. The shear strength of the sheet metal is 500 megapascal. So we need to find out, calculate the smallest punch diameter. Smallest punch diameter. Is it clear? So you can see here, if I calculate the punching force required first, punching force, that is FP. So FP is nothing but this is yield shear strength into pi d into thickness. Yes or no? So and the crushing strength is already given here, and the shear strength is also given here. Yes or no? So if I consider crushing strength, crushing strength, so can I say the crushing stress induced is nothing but the crushing load over crushing area, that is pi by 4 d square. Yes or no? So let's see, this is equation 1 and this is equation 2. And let me see, this expression can also be written as AC is equal to sigma C into pi by 4 d square. and this crushing load is remains same as you calculate in the punching force actually required. Correct? So PC is equal to FP. So from this we can write tau s into pi d into t is equal to sigma c into pi by 4 d square. Is it right? So from this if I calculate, so this pi is cancelled out with this pi, d is also cancelled out with this t. So the t is nothing but it can be written as tau s 4 tau s into t over sigma c. So now if we put these values here, so 4 into 500 into thickness is already given, that is 2. And yes, if I use factor of safety, if we use factor of safety, so simply instead of writing 1500 megapascal, instead of this we write 1500 by 3. So if you calculate this, then you can see here, this is 8 mm. Is it right? This is 8 mm. So the correct answer is 8 mm. Option C is the right choice. Next, the shear strength of sheet metal is 300 mm. The blanking force required to produce a blank is 100 mm diameter and 1 mm sheet thickness is close to. So once again you can see here tau s is given, that is 300 megapascal, and blanking force required to blank of diameter. So diameter of the blank is 100 mm and the sheet thickness is 1.54 mm. Correct? So here we need to calculate the blanking force required, that is FP in kilonewton. So FP is nothing but this is equal to tau s into shear area. FP is equal to tau s is given here 300 megapascal. Shear area is pi into d, that is 100 mm, and the thickness is 1.4, sorry 1.5 divided by 1000 for getting this value in kilonewton. So if you simplify this, then you can see this is cancelled. So 30 into 3.14 into 1.5. Here we get 141.3 kilonewton. So the correct answer is option C. Okay, so next question you can see, in a shear cutting operation, a sheet of 5 mm thickness is to be cut along the length of 200 mm. So this the total length of the cut is 400, but we need to cut only up to this length. So when you if you need to cut this length, so obviously you need this. Let's say this is shear prime. So first we need to calculate this value, how much shear is actually required. The cutting blade is 400 mm long, and the zero shear s equal to 0 is provided on the edge. The ultimate shear strength is 100 megapascal. Correct? The penetration to the thickness ratio is 0.2. So P is given here, that is 0.2 into sheet thickness. Penetration to small p by t is given, sorry, capital P by t is given, that is 0.2. So P is equal to 0.2 into thickness, and 0.2 into thickness is given, that is 5 mm. Can I say this is 1 millimeter? Is that clear? So this is penetration which is given in the question. So what we need to calculate, a shear of 20 mm is now provided on the blade. If this is 20 mm, assuming force versus displacement curve to be trapezoidal, the maximum force required. So obviously when we have a sheared punch, then the force required for shearing is nothing but this is tau s into shear area, that is, and since this is a linear cutting, so can I say the length of to be cut into shear length into thickness over shear. Correct? So this, and what about shear? Let's say this is S prime, because the total shear is given, that is 20 mm, but the length of the blade is 400 and we need to cut a length of 200 mm. You can see here LS is given, that is 200 mm. So for this we need to calculate S dash. So simply if I apply this is a similar triangle property, you can say this is a triangle, correct? This length is 200 and the total length is 400 mm, and this shear is 20 millimeter. So how much shear prime we have? So can I say shear prime is equal to 200, sorry, 20 by 400 into 200. So S prime is nothing but this is 10 millimeter. So now you just put these values here, then you will get the answer. F is equal to tau S is given, that is 100 megapascal. Shear length, that is 200. Thickness is 5 millimeter. Yes or no? Is that right? And yes, penetration. Yeah, yes, we need to multiply penetration. Instead of T, can I write directly? This is capital P. This is capital P. Why I am writing capital P? Because capital P is nothing but small t into small p. Thickness into percentage penetration is gives us total penetration, that's P. So instead of using this thickness, can I use directly 1 millimeter over 10? So if you simplify this, then here we get, and in kilonewton, so can I divide with 1000 Newton? Sorry, 1000 value. So this two zeros cancel out with this, and this zero and this zero is cancelled out with this. So simply here we get, yes, something is missing here. Something is missing here. Length is 200. Okay, so let me check, no issue. Correct. S dash is remain correct, no issue from this. So let me check the formula once. Okay, so this is incomplete formula. Yes or no? This is the incomplete formula. Is it right? Is it right? Why it is incomplete? So it is incomplete because you can say this is tau s into length into this p. Correct? Percentage of penetration only. So this millimeter is cancelled with this. So here we get Newton per millimeter answer. That's why it is wrong. So let me check this formula again. But the remaining calculation is correct. Is it right? So let me see. Let me see. The shear force required is nothing but this is tau s yield shear strength into length into thickness. Is it clear? Length into thickness. This is the maximum force required over divided by the this is the maximum force required into the amount of shear. Yes or no? Into the amount of shear. So you can see here, if I see this question, so it can be written as F. This is called F into PT. We need to multiply PT here, or simply you can say capital P divided by shear. Yes or no? And sometimes this shear can also be written as plus P2. Is that right? So here I am neglecting this value, that is small s, sorry, small pt. So now we can get the correct answer. Correct? So this is 100 into length is 200 into thickness is 5. And what about pt? You can see this 0.2 is nothing but this is small p. So instead of writing pt, can I use capital P? And here I am writing one comment, that is capital P is equal to small p into t. And this capital P by T is given here already in the question. Correct? So this is 1 mm over the shear is 10. So now if I also divide with 1000, then you can see here we get this is 5 kilonewton. Yes, 5 kilonewton. This is the right answer. Option A is the right answer. Correct? So actually we are not using this value. And if I write this formula also, so this formula can also be written as this is F max into capital P over S. And what about F max? This tau S into L into T. This is F max, correct? So this formula can also be used like this. Okay, so this is another part. So in a shear cutting, this is the second part of this question, I think. A shear cutting operation, a sheet of 5 mm thickness is to be cut along the same question. What we need to calculate, assuming this your force versus displacement cut to be rectangular, the work done in joule. Here we need to calculate work done. So work done is nothing but this is F max into penetration. And what about F max? This is tau s into length, shear length into thickness into penetration. Correct? So tau s is given that is 100, length is given that is 200, and thickness is given 5, and PT is 1 mm. I already calculated in the previous slide. So same, and this is in Newton millimeter. So sorry, millimeter. So this value gives us Newton, and this is millimeter. So the unit is Newton millimeter. So we need to convert this unit into Newton millimeter to meter. So simply here we divide with 1000. So here we get Newton in millimeter, or simply you can say joule. So when you simplify this, then definitely you will get this answer. 20 into 5, that is 100 joule. 100 joule. Correct. So work done. What about work done? You can see if I talk about this question, so simply you understand this concept. Let's say suppose this is a sheet where you need to cut. Correct. And for cutting by using flat cutting edge, we need to penetrate our tool up to this. Correct. We need to penetrate. This is a cutter and this is a blank. When you penetrate this tool up to this depth, which is called as P, capital P, that is P into small t. Correct. Then the entire sheet can be cut. Yes or no? So we need to calculate energy required for this much amount of cutting. That's why I'm writing this is the maximum shear force required and how much penetration or how much tool is traveled. So work done is nothing but this is force into tool traveled, yes or no? So the maximum force is tau s into ls into t, and the length of maximum traveling of the tool, that is p. Correct? That's why multiplying p, yes or no? So I hope you will understand this concept. Okay, so let's see another question. In a deep drawing of a cup, blank shows a tendency to wrinkle up around the periphery, that is flange, the most likely cause. So the for wrinkling, the most likely cause is insufficient blank holding force. For wrinkling, the main reason behind this is insufficient blank holding force. You must remember this point. So let's see which one is the correct answer. Buckling due to the circumference of compression, not runs. Incorrect answer. High blank holder pressure and high friction. High blank holder pressure. This is causes tearing defect. This is called as tearing defects. Tearing defects means, let's say this is your flange and this is your cup. Correct. So when sometimes when you have very high blank holding force, then some tearing takes place between flange and wall of the cup. High temperature causes increase in circumferential length. This is incorrect answer. Buckling due to circumferential compression decreases blank holding force. Yes, this is the right answer. This is the right answer. Is it clear? Okay, so let's see this question. The force required in a blanking operation of the low carbon steel is 5 kilonewton. The thickness of the sheet is T. The diameter of the blank is D. So for same work material, if the diameter of the blank part is increased by 1.5 D and thickness is reduced by this, the new blanking force. The blanking force is nothing but this is tau s into pi D into T. So can I say the force is directly proportional to D into T? So simply you see F2 by F1, this is equal to D2 into T2 by D1 into T. So simply can I write this is D2 by D1 into T2 by T1. So from this the F2 is equal to F1 times D2 by D1 into T2 by T1. So now if you put this value here, so what about F1? This is 5 kilonewton. And what about D2 by D1? This is 1.5. So can I say this is 1.5 and this is 0.4. So now if you multiply, so this is 3 kilonewton. 3 kilonewton. After calculating this, you will get 3 kilonewton. So the correct answer is option A. So what about this question? Match the item in column 1 and 2, wrinkling defect, insufficient blank holding force, orange peel defect. This is planar large grain size. Stretcher strain, earring defects, planar anisotropy. So you can see for P we have fourth option and 4, and Q we have 3 option. Yes, so the option D is the right answer. Correct. Option D is the right answer. So let's say this question. A 2 mm thick metal sheet is to be bent at an angle of 1 radian with a bend radius of 100 mm if the stretch factor is 0.5. So you can see actually the bend allowance is nothing but this length is called as bend allowance. Correct. So the bend allowance is nothing but this is R plus half of the thickness times alpha into stretch factor, that is K. Correct. So what about the radius of curvature? This is 100 mm plus thickness is nothing but this is 2 mm. So 2 by 2 into alpha is nothing but this is 1 radian, and bend allowance is given, that is 0.5. Sorry, stretch factor is given 0.5. So simply 101 into 0.5. So this is 50.5. So this is, so the band allowance is nothing but we have this relation only, R plus T by 2 into alpha into K. Stretch factor is 0.5 and 1 radian angle we have. So if you multiply this, so okay, yes, you just leave it, leave this term. Correct. R plus, this is a band allowance. And what about stretch factor? What about this stretch factor? Let me check. Okay, so you can see here. Okay, so here we have this relation. Yes, yes. Now the band allowance is nothing but it can be written as alpha into R plus stretch factor K into T. Correct? So this is 1 degree and this is 100 plus 0.5 into thickness 2. Correct? So this is 101. So the bend allowance is 101 millimeter. So this is very simple formula, R times. Obviously this is called as bend allowance. We need to write this length. Yes or no? Okay, so what about this 10 mm diameter hole are to be punched in a steel sheet of 3 mm thickness. Shear strength of the sheet metal is this. Penetration is 40%. Shear provides on the punch 2 mm. So you can see here in this question, the diameter of the blank is 10 millimeter. Are punched in a steel sheet of thickness 3 millimeter. Shear strength of the material is 400 megapascal and the penetration, that is small p, 0.4, 40% means 0.4. Here of the punch is 2 mm. The blanking force required, so you need to calculate blanking force in kilonewton. So the blanking force is nothing but this is tau s into, first you need to calculate maximum force, so tau s into pi d into thickness. This is maximum force into penetration over shear plus penetration. Is it clear? So simply you can see here, this is 400 into pi into 10 into 3. And what is capital P? So the capital P is nothing but this is small p, penetration into sheet thickness. So this is 0.4 into sheet thickness is 3 mm. Punch already given, that is 2 mm plus 0.4 into 3. So now if we calculate this, then here we get, and obviously we need to write in kilonewtons, so simply we divide with 1000. So let me see what is the correct value. So 400 into pi into 10 into 3 into 1.2 over 1000 over 3.2. So this is, if we use, sorry, here we are not using, because when you use this term, then the answer will not be matched with any options. So instead of writing this, simply we use only S, not P. Correct? So S is nothing but this is 2. So once you use this, then here we get 22.608 kilonewton. And if you put P in the denominator, then the answer will be 14, and which is not available in the option. That's why I'm choosing this formula. Otherwise, S plus P is the right formula. Yes or no? So according to this, the correct answer is option A. Okay, so what about this question? A metal disc of 20 mm diameter is to be punched from sheet of 2 mm thickness. The punch and the die clearance is the required punch diameter. So this 20 mm diameter is to be punched. A metal disc. So you can say this is a blanking operation. This is a blanking operation. Correct? So in this, the diameter of the blank is equal to diameter of the die, which is 20 mm, and this is fixed. So we need to calculate diameter of the punch. So diameter of the punch is nothing but diameter of the die minus 2c, and this is 20 minus, what about clearance? 3% of sheet thickness. Sorry, the punch and the die clearance is 3%, the required punch diameter. So can I say this is 3 by 100 into sheet thickness, that is 2. So when you solve this, then here we get 19.88 mm is the right answer. So the correct answer is option A. Next, you can say this question. A cell of 100 mm diameter and 100 mm height. Okay, so here we make a cup whose height and diameter is remain same. Its diameter is 100 mm. Height is also 100 mm. And the corner radius R is equal to 0.4 mm. So the cup drawing, the required blank size. So once again you check, the diameter of the cup is greater than 20 times of corner radius. Then we use d is equal to square root of d square plus 4dh. So if I check this, so this is 100, which is greater than 20 into 0.4. This 100 is greater than 20 times 0.4. Yes or no? So simply we use this relation. So I'm not writing this. Directly we can use this formula. Yes or no? So once you use this formula, so now you just put the value. So this is d square, which is 100 square plus 4 times of 100 into 100. This is nothing but this is 100 root 5. Yes or no? So from this, if I calculate, then here we get 223.60 millimeter. So the correct answer is option C. Identify the stress strain in the flange portion of a partially drawn cylindrical cup when deep drawing without a blank holder. So if you perform deep drawing without blank holder, the tensile in all three directions, no stress in the flange at all because there is no blank holder. Tensile stress in one direction, compressive stress on the other. So if this is a blank, and if you apply force with the punch, this is punch and this is blank, correct? So obviously it can be drawn like this, correct? It can be drawn like this. Is it right? So in this case, when there is no punch, so in the flange region, you can see in the flange region, there is no stress induced. There is no stress induced, correct? Because there is no blank holder. So the correct answer is option B. A 50 mm diameter disc is to be punched out from the carbon steel sheet of 1 mm thickness. The diameter of the die should be 50 mm diameter disc. So this is a blanking operation. First, write this is a blanking operation. The blanking operation. So in blanking operation, the diameter of the die is equal to diameter of the blank, which is equal to 50 mm, which is already given. So the diameter of the punch is nothing but this is diameter of the die minus 2c. So this is 50 minus. So you can say this option is wrong. And the carbon sheet thickness is 1 and the clearance is 3% of sheet thickness. So 1 into 3 by 100 into 2. Correct? So simply here we get 49.94 mm. This is the right answer. So there is no such option. So the correct answer is none of these. Okay, what about this? The thickness of the blank needed to produce by a power spinning of missile cone. The thickness is 1.5 mm and the half cone angle is 30 degree. So here we need to calculate the thickness of the blank. So the thickness of the blank, this is actually spinning operation. Thickness of the blank is nothing but it can be written as cone thickness. You must remember this formula, cone thickness over cos 2 alpha. Correct? So cone thickness is given, or spinning a missile cone of thickness 1.5 mm. This is given. This cos half angle is 30 degrees. So 2 alpha is 60 degrees. Yes or no? So cos 60 is nothing but this is 1 by 2. So from this here we get 3 mm. So the correct answer is option A. 3 mm is the right answer. A sheet metal with stock hardness is 250 HRC has to be sheared using a punch and die. Has to be sheared using a punch and a die having a clearance of 1 mm between them. If the stock hardness of the sheet material increases 400 HRC. So you can see here the clearance is equal to 0.0064 T into square root of tau. We already saw this formula, yes or no? And hardness is always proportional to strength. As you increase the hardness, the strength will also increases. So can I say the C is directly proportional to square root of hardness? Correct? So if 250 HRC we have, then the clearance will be 1 mm. So C2 by C1 is equal to square root of HRC1 by HRC2. Sorry, HRC2 by HRC1. Is it right? So simply you see this is 400 by 250. And C2 is equal to C1 is already we have 1 millimeter. So simply we can say this is 400 by 250 square root of this. So this is 1.26. 1.2649 millimeter. This is the correct answer. The correct answer. Correct. And this formula already we saw in the previous. Okay, so let's see. So this first, now you can see the end product obtained using a spinning process in the figure. The initial blank thickness is 2 and the blank diameter in millimeters. So you can see first if I talk about the spinning process. So in this you can see here we have a mandrel which is looking like this. This is the mandrel, correct? Mandrel. Like this, correct? And this is a seat from which we the this object, yes or no? And this is called as a blank, the blank. And have a rod. With the help of this we can hold this shape, yes or no? And obviously this mandrel can rotate about this axis. And let's suppose if this mandrel is fitted on the lathe machine chuck and it can rotate about its own axis, and by this rod you just push this metal, then it will deform like this. Then it will deform like this, yes or no? So this is called a spinning process. This is called a spinning process. Is it clear? So simply here we see, if I talk about the length, let's suppose this is your object which is to be used by using a spinning process. This is your object. So obviously if I see it's a blank, then obviously the blank can be thing like this, yes or no? This is blank, and this length is nothing. You can say this is the slanting length of this object. Can I say this blank is bent into like this, then we get this shape. So this length is nothing but this is L, and this is L, and this is diameter which is D2. Yes or no? So the if I talk about the diameter of the blank, so nothing but this is times of L plus D2. So now the question is how to determine L. So if I draw a perpendicular from this, correct? So you can see this is nothing but this length is 45 mm and 30 mm, 30 degrees length is given. So we calculate this. Nothing but 45 over sine 30. Is it clear? So length, this length L is nothing but this is from this triangle. Can I say this, or simply you can say it can be looking like this. 45 is equal to L sine 30. Yes or no? So from this L is nothing but it can be written as 45 over sine 30. This is equal to 90 mm. And once you get this L, what about D2? You can see this is the diameter and this is one diameter. Yes or no? So simply the diameter of the blank can be written as 2 times of length, that is 90 mm plus 30 mm. Yes or no? So dB can be written as 210 millimeter. This is the answer. Yes or no? Okay, so let's see another question. The ratio of press force required to punch a square hole of 30 mm side in 1 mm thick aluminum sheet to that needed to punch a square hole of 60 mm side in 2 mm thick sheet. So let's suppose we have a square pocket. Yes or no? This is a square hole, correct? So this is first case and this is second case. Size is looking like this. So you can see here its size is, let's suppose this A1 which is to 30 mm, and let's suppose this sorry, 1, this is equal to 1 mm, and this is S2, which A2 is nothing but this is mm, and T2 is nothing but 2 millimeter. Yes or no? So from this, here we need to find out the ratio of punching force required. So you can see here the punching force is nothing but shear strength of the C2 perimeter of this square. So perimeter of the square is 6a times of thickness. This gives us shear area. Yes or no? So from this, can I say the punching force is directly proportional to AT? So P1 by P2 is nothing but this is A1 T1 over A2 T2. So put these values here, and here we get 30 into 1 over 3 into 2. This ratio gives us 0.25. Correct? So the correct answer is P1 by P2, nothing but this is 0.25, or simply you can write 1 by 4. Is it clear? Okay, so let's see another question. Match the following metal forming process with their associated stress in the workpiece. So if I talk about coining process, this is mainly used in the minting industry. So in this we apply compressive force. Wire drawing, in this we apply tensile force. So this S, this T. And if I talk about blanking, then obviously here we apply shearing stress. So this is Q. And in the deep drawing, we apply both tension and compression, R. So SPQR. So option A is the right answer. Next question. Circular blank of 10 mm diameter are punched from an aluminum sheet of 2 mm thickness. You can see circular blank of diameter here. The diameter of the blank is given which is equal to 10 millimeter. And this is a blanking operation, correct? And the thickness is also given, that is 2 millimeter. The shear strength of the aluminum sheet is equal to 8 megapascal. The minimum punching force required. The minimum punching force required means here we need to calculate P. Is it clear? So punching force is nothing but this is the strength of the sheet into shear area. And how we can write shear areas? This is the circular punch. In this we need to make a circular blank. The circumference of the circular blank is nothing but this is pi d. The circumference into thickness. This gives us shear area. Now you just put all the values here. You can write 80 into 10 into, sorry, 80 into pi into 10 into 2. And if I divide this value with 1000, then here we get this value in kilonewton. So after simplifying this, you will get how much? This pi times, let's cancel out with this is 1.6, and if you calculate this, then here we get 5.024 kilonewton. The correct answer is option C. Okay, next question, you can see which one is not a method of reducing cutting force to prevent the overloading of the press. You can say not a method. So clearance, providing shear on the die, this is the wrong answer because it reduces the actual force required. Provide shear on the punch, it also wrong answer because this is correct, because by providing shear on the punch, the shear force reduces, increasing the clearance. Yes, this is the right answer. Clearance may not affect the loading required for shearing or punching. Is it clear? So that's the correct answer is option C. Now you can see this question. Food cane, match the following product and manufacturing process. Food canes can be made either by deep drawing or it can be made by extrusion process. And if I talk about connecting rod, then obviously it is manufactured by forging, and metal foils are manufactured by rolling. And if I talk about more precisely, then the Sensmeyer mill is used for making of metal foils. Is that clear? So according to this, if I see the which one option is correct, so P3, P3, yes, and P4 also correct. So this is P3, P3, and connected around Q1 and R, that is rolling. Yes. So the correct answer is option A. The correct answer is option A. Is it clear? The correct answer is option A. For making canes, especially we use impact extrusion. use impact exclusion. Correct? Okay, so what about next question? A cup of 10 centimeter height and 5 centimeter diameter. A cup of 10 centimeter height and 5 centimeter diameter is to be drawn made from the sheet metal of thickness 2 mm. Thickness is 2 mm. The number of deduction necessary will be if limiting draw ratio is 1.9. Is it clear? LDR is given here 1.9. And if I talk about LDR, then this is nothing but this is diameter of the blank over diameter of the cup. Correct? Diameter of blank over the diameter of the cup. Correct? So first we need to calculate diameter of the blank. So nothing but as you know that here we have this relation. D square plus 4dh. What about this? D square. What about D square? D square is nothing but this is 10. Sorry, not 10. This is 5. 5 centimeter diameter. So 5 square plus 4 into 10 into 5. So from this here we get 25 plus 40 and 225. The diameter of blank. So obviously from this we get 15 centimeter. Yes or no? Here we get 15 centimeter. This is the diameter of the cup and this is the diameter, this 5 centimeter is the diameter of the punch. Yes or no? You can see here limiting draw ratio is already given here, that is 1.9, and if I say this is 15.15 over 5 gives us 3. Yes or no, which is greater than this? So limiting draw ratio actually tells us how much maximum drawing is possible. So 1.9 times 1.9, correct? If the diameter of the diameter of the hole is, sorry, diameter of the blank is 1.9 times of the diameter of blank, then it can be drawn in a one stage. So here we need at least 2 stages. Yes or no? Here we need actually 2 stages. Correct? Because here this ratio is 3, which is greater than the limiting value. So at least two step or number of 2 deduction required. The function of draw bead in the deep drawing operation. What is draw bead? Actually, you can see. If I talk about this is a, let's suppose this is a blank holder. So in this we have some projection like this, and if I talk about this top view, then obviously this draw bead is situated throughout the circumference like this. Yes or no? And similarly in the die, here we have hole like this. Correct? Correct, like this. We have this kind of drawing dies. You just think like this. This die. So obviously this draw bit is provided to the blank holder. This is blank holder. This is blank holder, and this is cup. Sorry, not cup. This is die. Is it clear? So and obviously here we also have hole like this. Correct. So the function of this draw bead is to balance the produce a balance between the amount of stretching and drawing. So when you need to make a cup is having flange, then we use this arrangement. Yes or no? And if there is no need of flange, this is your flange. If you make a utensil with flange, then we use this. And if you make cup only like this, then no need of providing this draw bead. So in this only you get a drawing. There is no stretching, but in this we have drawing as well as stretching, and for stretching we need to prevent the motion of the metal, and it is only provided by this blank holder. Yes or no? ब्लैंक होल्डर क्या करेगा, जब यहाँ पे आप ब्लैंक को प्रेस करोगे तो ब्लैंक होल्डर और रेडियल फ्लो को प्रिवेंट करेगा, की वजह से स्ट्रेचिंग भी होगी। तो यहाँ पे ड्राइंग और स्ट्रेचिंग दोनों ही होता है व्हेन यू मेक अ होल विथ फ्लेंज। एंड अगर आप विदाउट फ्लेंज होल कप बनाओगे तो यहाँ पे सिर्फ ड्राइंग होता है। तो द फंक्शन ऑफ ड्रॉ बीड इज टू प्रोड्यूस द बैलेंस बिटवीन द स्ट्रेचिंग एंड ड्राइंग। इज इट क्लियर? नेक्स्ट, इन अ ब्लैंकिंग ऑपरेशन द बेस्ट वे टू improve the smoothness and squareness of the edge is to, so smoothness and squareness is only possible if you provide optimum clearance. Yes or no? Have reduced gap between punch and die, increase the ductility of the seat, decrease the spring, the blank provides shear on the punch. Correct? So have reduced instead of reducing. If it is written here that is optimum, because if you have large gap then also you get the rough surface. If you have less gap then also you get rough surface. Correct? So if you have optimum gap then you will get the smooth and perfect squareness of the edges. Yes or no? The correct answer is option A. In a bending operation, if the modulus of elasticity is increased, keeping all parameters changed, the spring back will be. So spring back, whenever you increase Young's modulus, the spring back will also be this. Wall thickness of the drawn cup is controlled by ironing process. What is ironing process actually? You can see here. Let's suppose you have a blank. Let's suppose you have a blank, and here we have a die like this. Suppose you have stepped this die, then obviously deformation takes place like this. So through this you can control the thickness of the sheet. So called as ironing process. So the correct answer is ironing. Next, yes, this is a repeated question. So the correct answer for this is already I solved. Next, in a progressive die spring loaded stripper plate is used to clamp the stock until the punch penetrates twice the stock. This is wrong. Removes this wrinkle. This is also not its purpose. Automatic feeder plates release it. Wrong. Punch is completely withdrawn from the stock. Actually, you can see your blank holder. Let's suppose this is a blank and this is die. Correct? This is die and this is blank holder. Correct? So sometimes blank holder is not used. Instead of this, we just use stripper, called stripper. And now when you apply punching force, then obviously due to the punching force, this deformed material can, यहाँ पे क्या होगा, डिफॉर्म होगा विद द हेल्प ऑफ दिस पंचिंग फोर्स। एंड ऑब्वियसली आफ्टर डिफॉर्मेशन होगा क्या, कुछ इलास्टिक रिकवरी होगी जिसकी वजह से ये डिफॉर्म मटेरियल पंच को पकड़ लेता है। करेक्ट है? जब आप विड्रॉ करोगे तो ये भी साथ में इसके साथ विड्रॉ होना चाहेगा, तो इसको हम प्रिवेंट करने के लिए स्ट्रेपर यूज करते हैं। करेक्ट आंसर इज ऑप्शन डी। इन अ ब्लैंकिंग ऑपरेशन द क्लियरेंस इज प्रोवाइडेड। यस, दिस इज अ ब्लैंकिंग ऑपरेशन। सो इन द ब्लैंकिंग ऑपरेशन, the blanking operation the diameter of the blank is always equal to the diameter of the die, जो कि फिक्स्ड होता है। इसके रिस्पेक्ट में हमें diameter of the punch ये प्रोवाइड करना होता है। तो diameter of punch is nothing but diameter of the blank or minus 2c, that is clearance. So the clearance is always provided to the punch only. Get right? Next, the cutting force in the punching and blanking operation mainly depends upon obviously the shear strength of the material. Now, deep drawing a sheet, the value of limiting draw ratio depends upon, listen, the limiting draw ratio is always depends upon the thickness of the sheet. Is that clear? And what is LDR? I already told you the LDR is nothing but diameter of blank over diameter of punch. This is called as limiting draw ratio. Wrinkling is common defect. Yes, wrinkling is the common defect of deep drawing. Deep drawn component. Yes, wrinkling, orange peel, earring, all these defects are the common defects of deep drawing operation. Is it clear? So this is all about the sheet metal questions.